Hello. Welcome back. Chapter 3 on matter and a little bit of Chapter 20. So we're going to pick it up with the Chapter 20 stuff. We had left off talking about how to dissolve something and what the heat of solution was. Solutions can be in three different states. We can have what's called an unsaturated solution. In an unsaturated solution, what you're dealing with is you're dealing with a condition where there is plenty of solvent and you haven't reached the maximum amount of solute that can dissolve in that solvent. So in other words, if you had an unsaturated solution, if you dropped in a seed crystal, another chunk of solute, it would dissolve. If you had a saturated solution, with saturated solutions, now you've reached the maximum at which the material can dissolve, and that maximum is called its solubility. So if we've reached the solubility of a material, we've reached the saturation point. That is, there's no more solute that could dissolve in that solvent. So if we drop in a seed crystal, it just goes to the bottom and does not dissolve. Supersaturation is a rare condition. Supersaturation, people love to talk about supersaturation, but and although there are materials that can supersaturate, there's not a whole lot of materials that can supersaturate and become stable. And what I mean by that is for them to last very long. One of them that does last long is something called sodium acetate, and I'm going to show you that in the video. What supersaturation is when you reach your maximum solubility, if you heat the solution and then add in some more solvent and then allow it to cool undisturbed, no vibrations, no dust gets into it, anything like that, then you can temporarily create this condition, this unstable condition where you've actually exceeded the maximum amount of material that could dissolve. By heating it, you've increased its solubility. And what happens when it cools down is that particles like sodium acetate have a complex structure, and they don't line up very well when they're cooling down in order to precipitate and form a solid and go back down to the normal solubility. So all you have to do is agitate them a little bit. You can take a stirring rod and gently scratch it on the beaker side near the surface of the solution, and that will get the excess to precipitate out. Or you can add a seed crystal like they do in this video. Alright, so there they have their saturated solution. And that, I mean supersaturated solution. And what they're going to do is they're going to add a seed crystal. Now the seed crystal allows it to line up. And once the particles start lining up, they can line up and create a crystal lattice. So all of the excess that you dissolved at the higher temperature, now that it's cooled, now that the particles can line up, they crystallize out. So supersaturation is pretty cool to look at. It is an unstable condition, so right now that container that the person is touching should be hot, because you're going from an unstable condition to a stable condition, so it releases heat. So sometimes people call this hot ice, because it looks like ice, but yet it's very warm to the touch. See if they got one where they do the seed crystal. That's really what I want to see. Yeah, a whole mountain of sodium acetate. Good for them. Nope. Nope. Here we go. I think this is the one where they add the seed crystal to get it to line up. There we go. Add a little bit of the crystal. And now the particles can line up on it. And the excess above the maximum precipitates out. Pretty cool. But like I said, supersaturation, although, looks interesting, it's really not something that we deal with too much in basic chemistry because there aren't very many materials that actually can create a stable supersaturated condition. All right, so what is solubility then? Max solubility. A couple properties about it. First of all, different materials have different solubilities. Some things dissolve very well in water. Some things dissolve well in oil or alcohols. Some things dissolve well in acetone. So different materials will dissolve to different extents, and the maximum amount of solute that you can dissolve in a certain amount of solvent is called its solubility. Second property is this idea that like dissolves like. All right. So when in the last video where we had the solulysis, we had an ionic crystal. Well, ionic crystals have positive ions and they have negative ions. So we would say this is polar, and they were dissolved by water molecules, which have a positive end and a negative end, which are also polar. So like dissolves like. Polar materials are dissolved by polar solvents. Non-polar materials like dirt and oil and grease are dissolved in things like soap, which is composed of animal fat, because animal fat is non-polar and so is dirt and grease. So you wash your hands with soap. So the purpose of the water is to just knock the soap off of your hands so that you don't get chafing and knocks the soap into the sink and down the drain. All right, solubility chart calculations. All right, you would be given a solubility chart to use on the test. We don't expect you to memorize any of this. Let's copy and paste it though. We'll put that right there for the time being. And before I forget, because I don't normally do this, the like dissolve like thing, I want you to see something that is called polar protic, which means that it's polar, but it's not very strongly polar, and it's dissolving of styrofoam, which is in the same type of condition, a polar protic condition. My goodness. I was sex trafficked for years. Brothels are hidden in plain sight. Boy, the things on TED Talks when you're looking up styrofoam dissolved in acetone. Alright, so the acetone dissolves the styrofoam. Now, this isn't something I would advise doing at home. Acetone is highly flammable. It looks as though it's melting the styrofoam. It's not. Styrofoam, when it's created, is actually whipped with air to make it low density, and that's the air coming out of it. So it's not boiling. If it did boil, that acetone would probably ignite from the heat. And there you go, it dissolves a lot of acetone. Okay, let's get back to the business at hand. Solubility calculations. There are a lot of different ways to describe solubility. One of the ways we did it, the SI unit way, is to do molarity, which is moles of solute divided by liters of solution. The only drawback to doing that is that the volume changes with temperature. It expands at high temperature and it contracts at low temperature, so there is some slight differences in molarity based upon temperature. So a lot of times what they'll do is they'll describe it using masses. And this is just one way in your textbook to describe the solubility of something. So let's say we had this as a problem. We said, okay, we're going to use this chart, And they want to know what is the solubility of, I don't know, let's do potassium nitrate at 80 degrees Celsius. So we follow this chart up, and it intersects the graph here. Zoom in, it looks like it's right on the 170. We'll go with that. So what this graph is saying is that at 80 degrees C, our solubility is 170. So 170 what? 170 grams of potassium nitrate per 100 grams of water. And you can't tell with this graph, but I think that they intended the graph to be to have sig figs down to the one column. So I'm going to pretend that it does. But the truth of the matter is the way they drew the graph, it really doesn't. But here's how I want you to define solubility when you do a test question. Solubility will be grams of the solute over 100 grams of water. This is, of course, at 80 degrees C. Now notice the values on the chart. For dissolving a solid in liquid, most of them increase solubility with temperature. They dissolve better at higher temperatures than lower temperatures. That's another property of solubility. Solids dissolve better in liquids at high temperature. Why? Glad you asked. Dissolving a solid in a liquid solvent tends to be endothermic in nature. So again, the delta H for dissolving a solid in water, not always, but tends to be a positive value. Tends to be endothermic. And the delta H for dissolving a gas in a water environment tends to be exothermic. Well, here's a rule we're going to follow for the rest of the year in chemistry. Heat always favors the endothermic process. So the more heat you have, the better it is for the endothermic process. The less heat you have, the better it is for the exothermic process. So one of the problems with like fish tanks and dissolved oxygen for fish is that if you let the water get too hot in the fish tank, the oxygen actually bubbles out of the water and the fish suffocate. So you want to keep that fish tank pretty cool, not cold, but cool, so that you have plenty of dissolved oxygen in there. Alright, so suppose they give us a question like this on the test. Well, I'm glad they asked. First of all, I'm glad they asked because I already did the first question. What is the solubility of potassium nitrate at 80 degrees C? Well, we already answered that. So now they're saying, well, what is the solubility of that at 20 degrees C? Well, we would expect it to go down. So let's see what we get. Find 20, and then we go up to the potassium nitrate curve, which is right here, and it's a little less than 30. So I'm going to say maybe 28, 27 grams of KNO3 at that temperature. So when I write the solubility of it, I can write S for solubility, and then I'm going to write at 20 degrees C, is about 28 grams of potassium nitrate per 100 grams of water. Second question. How much potassium chloride will dissolve in 224 grams of water at 10 degrees C? Alright, so now they're asking us something different chemical, but we're going to approach it the same way. Let me just erase my solubility chart. We're going to find 10 degrees C for potassium chloride. Alright, so I go to 10 degrees Celsius, and I find the curve for potassium chloride, which is not listed on this chart because I normally use a different chart. Okay, so we're going to change it from potassium chloride to potassium bromide. We'll just roll with the punches here because we have potassium bromide there on the chart. So we follow this up from 10 degrees, and it's looking at, I don't know, 64, 65. Let's go with 65. Alright, so we know the solubility of KBr at 65 degrees C is equal to, coincidentally, 65 grams per 100 grams of water. Alright, so that gives me a conversion factor to use. So I can just use my technique. Start with what they give you. They're giving you 224 grams of water. We're going to multiply that and try to get the grams of water to cancel. And they want to know how much potassium bromide. Remember, we changed it. Let's go back and change this here. Potassium bromide, KBr. Make it look official. How much KBr? Well, we said that at that temperature, 100 grams of water would dissolve 65 grams of potassium bromide. So now the units cancel and we're left with grams of potassium bromide. So we can use solubility, since it has a numerator and a denominator, as a conversion factor. And I get 145.6. I think they want 3 sig figs here, but again, it's hard to tell with this graph. Alright, easy. Put a whole bunch of those on a test. Alright, last question for this video. Now, again, if we have solubility, that doesn't mean we have to use it the way we have it. We can flip that fraction because it is a conversion factor. Those two values are associated with each other. 100 grams of water did dissolve 65 grams of potassium bromide in the last problem. So in this problem they say, hey, how much water is needed to dissolve 87 grams of potassium nitrate at 40 degrees C? So again, we go back to our chart. We look up 40 degrees Celsius, and we find the curve for potassium nitrate, which is a little bit above 60. Looks like 63 grams per 100 grams of water. Alright, so I know the solubility of KNO3 at 40 degrees Celsius is 63 grams of KNO3 per every 100 grams of water. So we can use that. Start with what they give you in the problem. They're saying, hey, we need to dissolve 87 grams of potassium nitrate. Let's start there. Now, can we get grams of potassium nitrate to cancel and convert that to grams of water? And we can. We have the relationships right here. 100 grams of water, 63 grams of potassium nitrate. But that cancels, and we get our answer. 87 times 100 divided by 63, and we get 138 grams of water. Alright, so there you go. Some solubility properties, some solubility videos to check out there that I thought were kind of neat. Saturated, unsaturated, supersaturated, and then these calculations. Thank you very much.